So properties of liquids and solids. We talked about these real briefly way at the beginning. We'll understand them a little more now. So the gases, which we spent a whole chapter on, we talked about how those atoms and molecules are separated by huge distances. And in comparison to those, liquids and solids are in very close contact with each other. They're touchingly close. Okay, so they're very close. The difference between solids and liquids, because they're both touchingly close, the difference is the freedom of movement. The liquids, even though they're touching each other, they're free to move relative to each other. And so a liquid is fluid, right? It can change its shape. In a solid, the particles, whether they're molecules or atoms, are held in a constant position relative to each other. So in this classroom right now, you're all sitting in desks. And so this is the solid state of students. You all have some kinetic energy. You're moving, you're breathing at least, even if you're snoring. I don't actually see anybody sleeping yet, so that's good. But you're sitting next to each other, and Andrew is in front of Wyndham, and that's staying the same. So this is the solid state. You're close. Okay, now Andrew melted and moved, right, just to be ornery, because that's what Andrews do. But if we get out of our chairs and walk about like we were earlier, signing the attendance sheet and picking up exams and stuff, we're still close together, but now the shape isn't the same, and Andrew and Wyndham could be in different positions relative to each other. So that's the important difference between liquids and solids. It's important to remember that atoms in the solid state are still moving, but they're just vibrating, okay? So they're just wiggling around in place, and some people are, more fidgety than other people. Here's an illustration. Here we have an illustration of gases, and we see there's a lot of space in between the particles, and they're moving. They're moving fairly quickly, and they're just bouncing around. It's like a giant Pong game with multiple blips in it. In the liquid, they are now close to each other, but they're able to mill about. It reminds me of a cattle feedlot where all the cows are just, they're just kind of milling about. And in a solid, the particles are fixed relative to each other. So this one is always to the left of that one. So that would be like cows in the stalls, and Bessie is always next to Sally, because they're stuck in their stalls and they can't move away from each other, right? Any questions?
Is there any actual form of matter that exists between liquid and solid, like a semi-solid? Is there an actual technical term for it?
Not really. There are solids like glass. Glass is amorphous. It doesn't have a crystalline shape. This solid would be considered crystalline in that it has a regular repeating geometric pattern. Mm-hmm. And some solids do not have that. Glass is one of them. Rubber is another. If you look at old, very old, hundreds of years old buildings, and you look at the glass windows, you see that they're thicker at the bottom. And so, I haven't studied this, but I've heard this, that they say that glass is actually a liquid. It's just extremely viscous. And so the glass is just very, very slowly running down to the bottom of the window. But it's just happening so incredibly slowly that it takes hundreds of years to make just a tiny little difference. So yeah, you can have something that's kind of in between. Some things melt sharply and other things soften and then become a liquid. So yeah, you can have things in between. Not sure that you can really be in between the liquid and the gas. And Wyndham, we're not going to talk about plasmas. We're not going to talk about plasmas.
At the moment that the liquid molecules have enough kinetic energy to break the intermolecular bonds, then they break apart and become a gas instantly.
They would fly off, yeah, and we'll talk about evaporation in just a minute. So properties of gases, we've studied these probably more than you wanted to. They have low densities compared to liquids and solids. Indefinite shape, they're going to take on the shape of their container. They also have indefinite volume. They will take on the volume of their container. They will expand to fill whatever container you put them in. That means they're also compressible, and you can squeeze them and make them smaller. They have very weak intermolecular forces relative to their thermal energy. So the kinetic molecular theory said they have no attraction. Well, they do have attraction, but compared to their thermal energy, it's not significant, and so we are able to ignore it under many sets of conditions. An example is carbon dioxide. Liquids have high densities compared to gases. They also have indefinite shape, but they have definite volume. They cannot be compressed easily. So they have moderate intermolecular forces relative to thermal energy, and an example is liquid water. Solids are also going to have high densities and compared to gases. They're going to be relatively similar to the density of the liquids, though. They have definite shape and definite volume. They retain their shape regardless of what container they're in. They also retain their volume. They can be crystalline, in which the molecules have an order or a pattern to them, or they can be amorphous. Amorphous meaning without shape. And so the particles are disordered. It'd be like, if you have a bunch of kindergartners come in and you just tell them to sit on the floor. They're not going to sit in rows. Okay, but if you give them one of those fancy carpets with the circles and you tell them to sit on a circle, then they'll be ordered and they'll be in rows, and that would be a crystalline. So they have strong intermolecular forces relative to the thermal energy. An example is sugar. Sugar's a solid at room temperature. C12H22O11. Big molecule. Okay. So liquids assume the shape of their container because they can move around. I don't know how much detail we need to go through on all of these. Solids have definite shapes. Because the particles are fixed in place. They're vibrating, but they can't move relative to each other, so that's why they retain their shape. Any questions?